Hello everyone, it's May the 1st. Let's do this. Largest positive integer that exists with its negative, given an integer array that does not contain any zeros. Find the largest positive integer such that minus k also exists. What if it doesn't exist? No such integer, return -1. Okay. So, well, I think a map will work. You want to do a map? Basically, what we say is if it's a negative value, we put it in the map. We don't need a map because it's only from the maximum is 1000, so we can just put it as that, right? But of course, I need to also check. Now I don't want to sort, so we're just gonna go left to right. If I hit a -1, we just set 1 into what do we set it? We put it into its value, right? We put it into its value. So so if it's a -1, I'll put -1 into the position 1. So when I hit 1, I can see -1 was there. If it's a 2, I put 2 in there. So basically, as we go through, each time we hit a positive value or a negative value, we check that position, right? We check that position. If in that position we have an opposite there, then we're good, right? And if in that position it's the same value as myself, like if I have a -1 and I see another -1 and I check the position, it's already -1, then we'll ignore it. But if the parity is different, not parity, the positive negative, right, is different, then that counts, right? And you only need to count it once, because if it happens again, it doesn't really matter. All we want is to happen once. So in that case, let's try it. Thank you. Okay, so here's what I'm thinking. We can say C. I'll do it. We'll call it scene new int. Most one actually should be 1001 because the value is from all the way to 1000, right? So basically for n int n of nums, right? Int res equals 0. Actually, res should equal to -1, right? And we just say, if nums math.abs n plus n is equal to 0, okay? Then we say res equal to math.maximum res and math.abs n, right? If it's equal to 0, if it's not equal to 0, then we do nums math.abs and let's use a new variable, abs equal to math.abs, and now I don't have to do this so many times. We can just call it abs, and then we call it abs equal to n, right? And at the end, it will return res. Okay, let's take a look to see if this one's right. Sorry, syntax error. out of bound. Oh, it's not nums. It's seen. Oh man. I don't know why I didn't know. It's seen. Yep, looks about right. Let me add some comments here. What's this one? 2441. Okay, 2441. What do I say? I say record the previous occurrence of it's hard to say. I'm not saying anything. It's just this is the solution. That's it. I don't know what to say. You just record it, right? And then you add it, it becomes 0, that means it happens before it happens. Alright, let's try it. Okay. Not bad. Alright, I'm curious. It has a solution here, so what do they do? Root force O(n) squared. 2 pointers O(n) log n, because you have to sort. 2 pass hash set O(n). 1 pass hash set. Yeah, I think this is something that's similar. 1 pass bit set. I knew it. There gotta be something interesting here. Oh, okay. Oh, use a bit. Oh, instead of an array, use a bit. So basically, if it's a positive and if it's set, then they were good. Nice. That was good. Wait, why are you still using this? That's not bit set. Wait, what's the difference between this then? I thought it can make the space complexity lower. Oh, this is what it do. It's just plus 1024. Num plus 1024. I like my method better. Alright, anyway, we're doing this. Alright, next we're gonna do is this freedom. It's about freedom. Freedom trail. Right? It's I used the DP plus that. Alright, let's see, just go through the real quick. Oh, we have 2 DP solution. And we have I remember we have DP solution and we have the Dijkstra-ish solution. So I think what I said is I want to do it. Yeah, let's do it. So the DP solution will be, we do top down. Right, we do top down. So I think what it is given a index, right? I think DP is given an index on the ring, and I'll go through the key or no. Given the index on the key, I'll go through the yeah. Given the index on the key and the current index on the ring, I go through the ring, and each time I hit a match, I call that, right? I call that. And then keep going until the key is exhausted, right? Until the key is exhausted. And basically we're saying, given the index on the ring and the index on the key, how many steps, what's the minimum number of steps to reach the end? That's basically how it is. And I do not want to run Java on this at all. I do not want to run Java on this at all. Let's run this. 514, right? 514. Let's see. I mean, it's possible that this will not pass. Okay, let's go Python on this one. Python 3. All right, so what we need is from collection, func tools, right? Port, IO, cache. Okay, so what do we do here? We have a ring, we have a key. So we have we just do it right here, right? We say, oh, we need a, okay, def solve I, J, ring index and key index. Okay, key index. And we return an integer. And then we're gonna use at cache max size equals to none. Okay, so with this, we need to solve this, right? So we have the index and the index, and then we say if ki is equal to len key, right? Then we return 0. We're already done. Otherwise, we need to go through the entire thing for I, right? For IR in enumerate ring, because that's how many steps I need to take. And we need to find also the smallest steps, right? So steps shall equal to r minus I. Well, it depends, right? If no, ri and I. If ri is depends. So ri minus I, right? Ri minus I will be the step. Okay, ri minus I is a step, and that's one step. And then the other step is ri minus I plus the size, and then do a mod. Is that right? So it's like if one is at 0, the other at 4. So before, okay, plus length is 5 is 9. 9 mod 5 is gonna be 4. So no. So it should be I minus R. I minus R is what? Minus 4 plus 5 is 1. So yeah, I think that shall be the minimum of, I minus ki. No. Ring I, right? Plus, get here m equal to len ring and n equal to len key. Okay, so this will be n. This will be plus m mod m and ri minus I plus m mod m. Okay, so this is the number of steps I need to take, and then what I need to do is to find solve. Actually no, we should say if r is equal to key I, right? Then rest is master.inf, right? And then we say if they're equal, then rest shall equal to minimum rest steps plus 1 plus solve, because I move on to the ri and ki plus 1. And then we return rest at the end. Okay, then we return solve 0, 0. Okay, not 100% sure. This feels so simple. Maybe this will time out. Who knows? Is this right? Wow, this actually might be right. Wow, this actually might be right. Gosh, it's very simple. Mn m squared n at dp ri ki is the number of steps to reach the end of key when the current index on ring and key are ri and ki indices. It'll be funny that this one times out though. Let's see if it did time out. No, it does not. Simple, very simple. Holy crap. It took me like an hour, but look at this. It's as simple as it can get. Okay, so that's solution 1. We have solution 2. So solution 2. So this is also from the official solution. It uses a Dijkstra-ish method. So what do? We start from something, right? And then we go for all possible, and then among those I pick out the least, right? I pick out the, wait, hold on. well, we start from 0, 0, right? And then we check for the next one. Then we push it in, right, into a stack, not into a queue. And then in the queue, it is the first time that it reaches, right? And then we just count the steps, right? We just count the steps. So when we reach each position, so each node, right? Each node is a tuple of Ri and Ki, right? We use a queue to store the first time that Ri, Ki, to store the next node to visit, right? And we keep track of the smallest, right? The smallest possible steps to reach each node, right? To reach each node. And it is since we only care about the first time that a node is visited, because it has the shortest path, right? Shortest path. We don't need a separate map to keep track of the steps. We only need a set to check whether a node has been visited before. Now, it's the first time you reach it, which is good. Because the steps is always increasing. So the second time you visit it would definitely be more steps, unfortunately. That's actually not right, right? The first time you reach it, what if there is another way to get to your node? Yeah, what if there's another way to get to your node? You know what? I'm Dijkstra this. Fully Dijkstra this. Okay, so we use a queue, keep track of small. Then we Dijkstra this. So we need heap queue. Okay, so what do we need here? We need an array of array to keep track of the smallest steps, right? So we call it memo steps. Means steps. Max, okay, times n for this in range m. Right. Q equal to this. Put 0, 0 in it. Right. And then what? And then that's step 0. Right, so we put this is step 0. So as we go, pop out, and then we start him here. We check, go through everything. Yeah, we get the steps. And then we say if it's equal, then we'll, if it's equal and if it's smaller, then I'll push it in. Okay, so we say min steps 0, 0 is equal to 0, right? That's 0 step. Ooh, that's actually not really 0 step though. And I also need, that's not 0 step because, yeah, I think we shall do this. Step, Ri and Ki. Okay, so while Q, right, step Ri Ki equal to heap Q dot heap pop Q, right? Then for I, R, so we're gonna copy and paste this thing. Right. Steps. This is steps. This is current step. Current equal to this. If R is equal to this, right, then we say current plus 1, right, which will be your step, and your new steps is steps plus current plus 1, right? Steps plus current plus 1 will be your step. Then you need to check if it's smaller, right? Next step, right? Steps plus current plus 1. If next step is smaller than min steps I, right? Because we moved there, and then Ki plus 1. Then min steps I, Ki plus 1. Go to next step. And then heap Q dot heap push Q. We're gonna do next step. I, Ki plus 1. Don't do this. And we have to say if steps is not equal to min steps Ri Ki, continue, right? And now we keep going, and if it is, we say the first time that hey, hello. The first time that Ki gets out, maybe I should check it here, right? Smaller than, yeah, I should check it here. Right, if there's equal, then we go to the next one. Then we shall say, if, I think it should be this. If Ki plus 1 is smaller than n, and this, right? And this. So blah 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 blah. Is it the first time we reach? It should be the first time we reach, right? Yeah, it should be the first time we reach. If it's the first time we reach, then we don't even need to do like this. We would just say if, right, ki plus 1 is equal to n. Then we can break this whole thing. Not only break the whole, we can just return next. We can return next step. I mean, otherwise we have to break like two things. And then this return, I mean, there's nothing return here. I'll return -1. Because it always works, right? It always works. Yeah, it is a guarantee. So this is just, okay, let's try. Let's try. This is kind of my understanding of how this shall be done using Dijkstra. Is it working? No, it's not working. It's not working at all. Okay, what happened? We say only if the next step is smaller. Okay, so at the beginning everything is very big, right? And you start from 0. Okay, you get the steps Rn and Ki. You pop them out. Steps is not equal to. Ooh, I think it should be larger. Because I just basically didn't even go inside. Okay, that's not too bad, right? Not too bad. I think I'm missing like 1 count. I mean, I could have just let it finish, right? If I let it finish, all I need to do is go through the whole column and then find the smallest. Yeah. Okay, so I'm gonna change the idea. I will say, so it's not the first time, right? So we say if ki plus 1 is smaller than n and this, and then we keep going, and at the end we're gonna return. Ooh, that's the first column. That's the last column. Damn. Last column. Okay, that's okay. So res we go to max. For I in range m, right? Range m. So res equal to minimum res and min steps I n minus 1. And then we'll return res. Is that right? Oi, oi, oi. This is bad. This is very bad. Okay, so that's not what we want. I think we want to make it slightly bigger. Because you can reach, yes, I think it's the same problem we have earlier. You can reach the end position, but, right, but you can't keep going. So we should say if ki is smaller than, right, if ki is smaller than, then we go to the next one. Yeah, but we have a problem here. Because, yeah, ki is the last one, right? It's the last one. So you find out what is the current step to reach the last one. Okay. And then you add it to it. And you put in the next one. The next one won't go. So, okay, so this one, let's see. Just do this one tiny change. Okay, let's do it here. If this yep, this will work. Now, does this mean the first time we hit is going to be correct? Okay. Basically we're saying the first time that we get out, if ki is equal to n, then we return steps. So I don't even do all this. I just do this. First time we hit, there we go. Dijkstra. Dijkstra works as well. See, it's not that hard, right? But it's hard for me when I first tried it. Yeah, it's like very straightforward. Dijkstra. Every time you go through all the steps, we always try to find the smallest step to go. Oh. That's okay. All right, that's that. That's these two. I mean, I think this is similar. Yeah. Plus key length. I use key length as well. Okay, that'll be it. I'll end right here. And yeah, we still have this thing to deal with. All right, I'll see you guys tomorrow.